In this short talk, I would briefly show you the advantages of AFM in the imaging of those fenestrations. So what are those fenestrations? These are transcellular pores, which are in nanoscopic range in size from 50 to 350 nanometers that are gathered in sieve plates. So in these areas that are full of these pores. So this is, of course, electron micrograph, but it shows exactly what it looks like in vivo. So these cells are from liver capillaries. So there's a lot of things happening there. So the blood is mixed from the portal vein and hepatic artery is full of nutrition. And we commonly use a term of a filter named liver. So all of this blood must to be filtered out from the sinusoids to pass the layer of endothelial cells to reach hepatocytes. So how this transport is facilitated, and it's facilitated by those fenestrations in addition to endocytosis through this thin layer of cells which in the cell periphery has less than 200 nanometers. And it was hypothesized that this transport is through to exerting force, like perpendicular force to the sinusoid. It's because of the typical red blood cell's diameter is larger than the lumen of this sinusoid. So it was hypothesized that the blood cells must to squeeze through the sinusoid, exerting this perpendicular force to transport the lipoproteins through fenestrations to the microvilli of hepatocytes. And for over like 30 years, it was impossible to somehow demonstrate that it's happening until we reached that thing with AFM. So using quantitative imaging, but I think I may say that it's really similar to pinpoint. That's why I was so interested in the talk of Dr. Alexander Klassen previously. It's amazing tool for investigation of biological samples. So it allows you to distinguish between cell body and the interior of those fenestrations, which are transcellular pores. So you can reach the glass slides within the pore. So it has like two types of force curves, one which would be really steep and the second which would be less steep, dependent on if we see fenestrations or not. So as you could see, dependent on how deep you calculate the stiffness, then you can lose the signal or you can reach the great contrast between the glass slide and fenestrations. But that's not all. And what was already not mentioned, but I think is extremely important in this method, it's that it allows you to deform samples and create so-called, let's say, force tomography. So having the full recording on each force distance curve in each pixel point of the image, it allows you to reconstruct the image from the contact point up to the maximum loading force used in the experiment. So here you have the image of the contact point, and then you could see that those fenestrations can dilate in accordance to the loading force that is applied to the sample, somehow proving this forced sieving that it could happen, and it allows us to calculate, to quantify the force which is needed to enlarge those fenestrations. So the only limitation that we have in this method is the time required for one of these pixel points. So we divided our experiment into different setups. So in one, we have low resolution, not allowing us to measure the diameter of those fenestrations, but it allows us to track the whole cell or part of the cell really fast. So it's 15 minutes per frame. But if we can select one of these sieve plates and we want to focus on that, then we can reach much better resolution, see how those fenestrations appear, disappear, how they move, even see individual actin fibers here remodeling, where we have like 90 seconds per frame. And finally, we can focus on individual fenestrations, even measuring them even faster. So with this great tool, we addressed so-called in vitro pharmacology. So we wanted to test how those fenestrations respond to different drugs. And it's extremely important in the liver biology or liver pharmacology, because, for example, we know that paracetamol is toxic for the liver, so we can add different drugs and test them on individual fenestrations and individual cells on living cells because of the advantages of AFM. And our greatest images are shown here because they show individual fenestrations changed when we aimed for the spectrin. So we destabilized spectrin in those cells, showing that individual fenestrations can blink. We called it blinking. So it was open in one line during scanning, it was closed in the next line of scanning, and it was reopened again. So we noticed that those fenestrations can exist into open and closed state dependent on spectrin. But the disadvantage, the drawback of AFM is that we cannot provide any chemical information, let's say any information about the proteins that are involved in those reactions. That's why I entitled this presentation this correlative microscopy, because we wanted to find the same fenestrations using different nanoscopic technique. So with the improvement of optical nanoscopy, we can reach beyond the resolution of diffraction limit to see those fenestrations, for example, in D-storm, so in stochastic methods. So we labeled for spectrin red and actin green, and we show that we can see larger fenestrations, and we can also adapt the signal from spectrin and actin, somehow proving that spectrin is involved in this formation of fenestrations. But this method is limited to only fixed cells, so we cannot see any of those blinking using stochastic methods. But that was not all for us. We wanted to somehow prove that these methods can be used or cannot be used interchangeably. So we wanted to find not only 2 techniques, but we found 5 techniques, all with the nanoscopic resolution to address the same fenestrations in one-to-one manner. So firstly, we use SIM, so it's a structured illumination microscopy, which is also enabling to see the fenestrations. And this is a wet fixed, so formaldehyde fixed sample. The same cell was then dried, fixed dried, and prepared for electron microscopy with the same protocol as is normally used for electron microscopy, and we correlated those fenestrations in one-to-one manner. What we showed that in electron microscopy, we always see this 30% increase of the fenestration size. The same situation was with AFM. So AFM on wet fixed cells using glutaraldehyde and electron microscopy also showed great correlation of those fenestrations, but especially here when the more water is in the higher areas, then this dilation, this enlargement of fenestrations occur even higher, and we can also see this 30% enlargement. So to finally, to finally prove that this is because of the drying effect, we compared 2 wet fixed methods, so STED microscopy and AFM, showing that these differences disappear. So in general, in our recent paper, we compare all of these techniques, showing that, of course, electron microscopy is the fastest technique, so it should be used, and also SIM, it should be used when we have those dependent effects and large a lot of samples, but it has the resolution which is not the best one, or it needs additional drying that can change the size of fenestrations. But we propose this coefficient to recalculate, and we can interchangeably use different techniques when we apply this coefficient. And STED and AFM provide much better resolution, but they are slower techniques. But I think I don't have to convince you that AFM, of course, is the best technique, because it can be applied to living cells and also to fixed cells at any stage of sample preparation, and still provide great resolution at any of those points. But to be honest, it's really slow, so it requires a lot of a lot of measurements. Finally, to show that we can have this from living cells up to dried fixed cells, we also show living cells from the whole sample. So you can see with larger force, we can even reach the image of the underlying under the cell actin stress fibers. After fixation, this image is gone. But when we label those cells, we can then just compare those images of living and labeled cells, and we could assign actin to the image from AFM. So we can fulfill this drawback by additional chemical information about the proteins to the AFM. And finally, we can extrapolate this image to the previously animated 4D, so with time studies, to somehow provide this lacking information about the protein of interest. And that is the part that we are now focusing on. I would like to thank all of the collaborators, because to achieve all of this super resolution technique, I had to travel a lot between different companies and also different institutions. Finally, I reached even farther than the polar circle. Most of the SEM and SIM data were done in the University of Tromsø. So it's the farthest north university in the world. And I want to thank you for your attention, hoping for some questions. Thank you.